Okay guys, let's take a look at today's lesson. We're going to be working with rational expressions and dividing polynomials, two kind of different topics that we're combining together. So first, let's look at some vocabulary words. Basically, a fractional expression is the quotient of two algebraic expressions. I mean, that kind of makes logical sense. You don't have to memorize these vocabulary words. I'm not going to test you on them, but I'm just going to look at the vocabulary. What is it that we're doing? A rational expression. A rational expression is a fractional expression, but it's a little bit more specific. The numerator and denominator are polynomials. Okay, so that's a rational expression. And a compound fraction, or many times it's called a complex fraction, is a fraction in which the numerator, the denominator, or both of them are also fractions. You know, they're fractions inside of fractions. And so we really never, that's like a non-simplified form. We really never leave anything like that. If you see a complex or a compound fraction, we would certainly work to fix that. And that's one of our tasks for today. These theorems, these concepts right here, still, again, I'm not going to test you on them, but I think they're kind of interesting, and we will be working with them today. For the remainder theorem, what that tells us is that if we have a polynomial, p of x, and we divide it by this factor, x minus c, maybe the factor is 2, maybe, or, you know, the root will be 2, x minus 2, or whatever. The remainder is p of c. Okay, so this is math notation. Let's make sure we understand what this is saying. This is saying that if I divide a polynomial by x minus, say, 2, I'm doing the exact same thing as if I just did p of 2. And we know what p of 2 means, right? We would take 2 and sub it in for all the x's and get our answer. So they give you the same number. I think that's quite interesting. And synthetic substitution is kind of a takeoff on that. We can use synthetic division to evaluate a function. Evaluate a function means this thing, p of c. I could, you know, it's called synthetic substitution. I could use synthetic division and put 2 in the little box, you know, like we do synthetic division, and my remainder is going to be p of 2. So I think that's just an interesting side note on how that's related. We have the factor theorem, and it tells us that c is a 0 of the polynomial if and only if x minus c is a factor of the polynomial. And that certainly makes sense. We looked at that. The zeros and factors are related. They're the same, not the same thing, but they're related. If we looked yesterday at a 0 of 3, if you remember. So if we had x equals 3 as my 0, if I'm going to go back into a factor, I would put x minus in front of it. Right? We talked about that. So if I have a root and I want to have the factor for the root, I just put x minus in front of it, and I have the factor. And that's the same thing every time. Doesn't matter what the root is. Just put x minus in front of it. You are good to go. Okay? So those are the concepts we're going to be looking at today. Are there any questions on the concepts? Okay, so we have a few examples on the second page. So let's flip over there. And so let's look. Oh, those look exciting, don't they? Woo! 1a is a complex fraction. Now, I'm going to tell you, I guess I'm a little boring. I simplify these complex fractions the same way every single time. There are no changes. There are fancy things you could do to simplify it. You could come up with a particular fraction that you could just multiply by to simplify. There are a lot of fancy ways to do it, but I am boring. I do the same thing every time. What I do is I take the numerator, and if there's a fraction inside of the numerator, I just find a common denominator and add them together and get one fraction. If there's a fraction in the denominator, I just find a common denominator, add them together, get a common fraction, and then I fix my complex fraction. Same thing every single time. I don't vary. I think that helps me to have that process in place instead of trying to come up with some unique thing to multiply by to make it faster and disappear quicker. I just want it to be right, so I'll just do the same thing every time. So let's look at this one. The numerator does have a fraction in it, so we need there are 2 of them, so we need a common denominator. So my common denominator, as I'm sure we are very, very familiar with finding common denominators for fractions, it's going to be a little bit of a mess. It's a times a plus h. I think we all recognize that a doesn't really help us any, right, in a smaller denominator. So my denominator is a times a plus h. And in this first fraction, I would be missing the a. minus, then I have a times a plus h, and in the second fraction I'd be missing the a plus h. All that is over, and I'm going to go ahead and make it a fraction, h over 1. Okay, so one of the most common mistakes that I see is when we're subtracting here, students may forget to distribute the negative to both the a and the h. So I want you to be cautious. I don't want that to happen to you. So this subtraction sign would go to both of those a and h. So let's go ahead and do that. So a minus h over a times a plus h, and that's over h over 1. Okay, I hope we can see from that that the a's are going to go away. And I'm going to be left with negative h over a times a plus h all over h over 1. Okay, so I have accomplished my first goal in these problems, which is to get one fraction over another one. That's what I do. I have one fraction over another one. Now I'm going to flip and fix the complex fraction. Let's talk about it from basics. I have one fraction divided by another fraction. We learned in middle school, right? When we're dividing fractions, we don't want to do that. We would rather multiply by the reciprocal. Remember that? So instead of doing this fraction divided by that one, I'm going to do this fraction times the reciprocal of that one. I mean, that's how we learned that. So I have negative h over a times a plus h times 1 over h. I'm just using my rule from many years ago. So I hope we can see that these h's would cancel out, right? And I would be left with negative 1 over a times a plus h. Now you can leave the a times a plus h, you can leave it factored, or you can multiply it out. It's really your choice. They both would be equally simplified, so it's up to you what you want to do. I typically would leave it. I don't want to do extra steps if it's not required, and it's just as simplified in that form. Okay, so that's our very first one. Are we okay with that one? Okay, so the next two, oh gosh, those are even more exciting, aren't they? They're fantastic. Let me tell you where they come from, because they really come from a process that we do in calculus called the quotient rule. That's going to be a fun rule, right? I bet you can't wait, right? The quotient rule, when we do the quotient rule, we get this kind of stuff. Now, the calculus part of it isn't that bad. I mean, you're thinking, oh my gosh. I mean, it's really, to be perfectly honest with you, some students get messed up on the algebra part in calculus, not the calculus part. It's the algebra part. Certainly not acceptable to leave things like this. That's a big mess. We have to simplify it. Okay, so we're going to practice on simplifying these types of expressions. Those, again, are the types of expressions that you will get next year when you are doing the quotient rule. So let's work on that. Let's work on this first one. It's going to involve factoring. And so we're going to look for a common factor. And if you see this, these two right here are common factors. Those are the same factor. I have two terms. I have this term and this term. Terms are separated by addition and subtraction. So I'm going to factor one of those out. I know that's kind of crazy, but let's look at a simpler problem. What if I had x squared minus 3x and I wanted to factor, do a GCF? You would be able to do that without even thinking, wouldn't you? You would know exactly what to factor out. How do you know what to factor out? You know x is common. How do you know that you're not factoring the x squared out? Well, because, I mean, you do it without thinking. You factor the one with the smallest exponent, right? The 1 is smaller than the 2, so I would factor that out. That's what I would do here. And then I would divide x squared by x. And again, you do it without thinking. How do I divide x squared by x? Well, I subtract the exponents. 2 minus 1 is 1. Right? That's how I'm dividing. Okay, so that's a much simpler problem. This is more complex, but it's the exact same concept. So how do I determine which one of these factors to factor out? I choose the one with the smallest exponent. Which is smaller, a half or a negative a half? Well, a negative a half is smaller. That's the one I'm going to factor out. So let's do that. We'll pull it out front. I have 1 plus x squared to the negative 1/2. Okay, when I factor, I divide. I am dividing. All right, so I'm going to show you up here what's actually going on. I'm taking 1 plus x squared to the 1/2, and I'm dividing it by 1 plus x squared to the negative 1/2. That's what's going on. I am dividing those. Factoring is dividing. We need to remember our exponent rules. I know we know and love those, right? They never go away. So when I am dividing common bases, what do I do to the exponents? I subtract them, right? So I would have 1/2 minus a negative 1/2. 1/2 minus a negative 1/2 is 1. So what I'm going to be left with inside of here is 1 plus x squared to the first power. That's what happens when I divide 1 plus x squared to the negative 1/2 out of 1 plus x squared to the 1/2. Okay, I hope that's as clear as I can make it. It's all we're doing is dividing. So when I divide this out of the second term, I am just left with an x squared. Okay, are we okay so far? So I chose what to divide out by it's the smallest exponent, and then I'm actually physically dividing. If you need to write this step out, I encourage you to write that step out, whatever makes it clearer to you. So now we have a couple of things going on. So we have two common bases. Still, I have this base and this base. I would want to combine them together. So this one is to the negative 1/2 in the numerator. I want to bring it together with this one. You recall what we would do? We could leave it in here. We could subtract. I could pull this down and make it a positive 1/2, couldn't I? Because it's a negative 1/2 in the numerator, if I moved to the denominator, wouldn't the sign change and be a positive 1/2? Okay, so let's think about what that would mean. So we're over here. I would have 1 plus x squared to the 1/2 times 1 plus x squared to the 1. Again, more exponent rules. What do I do when the bases are common? I'm multiplying. I would add the exponents, right? So what I'm going to be left with here, let's see if I can fit it over here, in the denominator is 1 plus x squared. So we know 1/2 plus 1 is 3/2. That's what I would have in the denominator when I bring this one down. And then it's a matter of cleanup. I need to clean up this mess over here. Combine like terms. So 1 plus x squared minus x squared is simply a 1. And that would be my answer. Okay, we okay with that? Okay, we're going to do one more similar to that, like quotient rule. This would be something we might get on the quotient rule. So let's look for some common factors. Let's see, I have a x plus 2 and an x plus 2. Those are the same. Okay, I also have an x minus 3 and an x minus 3. Those are some common factors that we're going to have to divide out. Alright, so let's do that. So let's look at the x plus 2's. Again, I choose the one with the smallest exponent. Right, I have a 2 and a 3. I'm going to choose the one with the 2. So I'm going to pull out here x plus 2 squared. Now let's look at the x minus 3's. So I look at the x minus 3's, I compare them, I choose the one with the smallest exponent, x minus 3. Open up my parenthesis. So we're going to be dividing those out of each term. So my x plus 2, so let's work on this first term. I have a 3, that stays there, right? That doesn't come out. This x plus 2 squared came all the way out, didn't it? But how many of the x minus 3's do I have left over? I have one of them left over. I have one x minus 3 left over. Okay, are we okay with that first term? Now let's divide out of the second term. So I have a minus, and I have a 2. The 2 is there. Now let's look at the factor. So I have an x plus 2 cubed, but I pulled out an x plus 2 squared. So I have one of those left over, don't I? I have an x plus 2 left over. The x minus 3 is completely gone. Okay? And that's all over x minus 3 to the 4th. Okay. How are we on the factoring part? Okay? So what I'm going to do, just kind of writing, I'm going to distribute the 3 and the -2. I'm going to distribute this like right above it, just really for time's sake and space on the board. So 3 times x is 3x. 3 times -3 is -9. -2 times x is -2x. -2 times 4 is -4. So I'm just going to kind of do that so we can combine like terms. Okay? All right. So let's kind of work. Look here, I have this and this, right? I want to combine those together. I'm really looking to shrink this and simplify. If I combine these together, do we clearly see what would happen? Right? This would be a 1, that's a 4, so that would turn into a 3 at the denominator, right? So we're okay with that. All right, so let's do that. So I have an x minus 3 cubed down here. And in the numerator, I still have that x plus 2 squared. That's hanging out there. Let's kind of clean this up. 3x minus 2x is x. And -9 minus 4 is -13. I would encourage you to leave it factored like this. There's really no need to try to multiply it all out. It just will, perhaps you may make a mistake, so I would really encourage you to not do that. Just leave it alone. Okay, so we're factored. So there's some examples on simplifying rational expressions. How are we doing with that? We okay? All right, let's move to division. So on division, we would have done this last year. It's going to be long division. So I'm going to set this up. Notice I'm missing the cubed term. So I need to put a 0 in for it. Remember how we did that last year? I'm going to put a 0 in for it. So I'm going to divide by 2x squared minus x plus 2. I'm dividing 8x to the 4th plus 0x cubed plus 6x squared minus 3x plus 1. Okay, so we're dividing. So I'm going to remind you how to divide. We take the first term and the first terms. So what I do is I try to think, well, what would I have to multiply 2x squared by to get an 8x to the 4th? I mean, that's how I divide. I think about it as multiplication. What would I have to multiply 2x squared to get 8x to the 4th? Well, I'd have to multiply by 4x squared, wouldn't I? And I typically put the x squared over the x squared on the fraction bar. Do I have to? No, I don't. I just like to. You don't have to. You can put it anywhere you want. But I usually just put it, right above the x squared term. So now let's multiply back out. 4x squared times 2x squared is 8x to the 4th. 4x squared times a negative x is negative 4x cubed. 4x squared times 2 is 8x squared. I always draw a line and parentheses and put a subtraction there because for the life of me, if I don't do that, I will forget to subtract. It's really important. This is just regular division, just like you've been doing for years. It just has variables in it. It's the same thing, it just has variables in it. So let's subtract. Let's see, the 8x to the 4th go away. A negative, that gives me 4x cubed. And 6 minus 8 is a negative 2x squared. Okay, now I bring the next term down. Let me start again. This time I have to think, what would I have to multiply 2x squared by to get a 4x cubed? That would be a 2x, right? So 2x times 2x squared is 4x cubed. 2x times negative x is negative 2x squared. And 2x times 2 is 4x. Okay, we go ahead and put it like that. I subtract. First two terms go away. Negative 3 minus 4 is a negative 7. Bring my next term down. And I can't divide anymore, can I? This 2x squared won't go into the 7x. So that's my remainder. And this is how you must write it. We don't do that R thing, okay, because we do this in calculus. We do this division in calculus, and this is how we need to write the answer, what we got. So the whole part is 4x squared plus 2x. That's the whole part. The whole part is the part that's up here. My remainder, I always put in a plus. I don't care what the sign of the remainder is. I always put a plus. If you do that, you will not mess up. Then I put the remainder, which is negative 7x plus 1, over the divisor, which is 2x squared minus x plus 2. That's how I need you to write your answers for division. Just like that. The whole part plus the fractional part. Okay? Hopefully that's a good reminder on division. Are we okay with that? Okay. Okay, the last problem. So on this one, we are given a 0 and we're asked to find all the other zeros. Now there's a couple of different ways you can do this problem. You could do synthetic division and divide the 3 minus I out of it. It'll be complex. Then you can divide the 3 minus I out of what you have left over and clean it up, but it's quite intense. I actually prefer something a little different. Okay, you can do that if you want to. That is fine. That's probably the traditional way to do it. But I don't want to deal with the imaginaries like that. I just don't. So what I'm going to do is I'm going to take this imaginary and its conjugate, and I'm going to go ahead and find the quadratic that goes with it. So I have the 3 plus I and 3 minus I. I'm going to use that formula, x squared minus some x plus product. I mean, that's what I'm going to do. And then, so I need to add these together. The sum of those would be what? 3 plus 3 is 6. I minus I is nothing. The product, so let's go over here and do a little scratch work. It's 3 plus I times 3 minus I. So we do 3 times 3, which is 9, right? Outside, inside go away. That's the beauty of a conjugate. Minus I squared. And we know I squared is a negative 1. And a negative 1 would be a positive 1. So my product would be 10. So my plugging into this formula, I would have x squared minus 6x plus 10. I'm going to divide that out of my equation. I'm dividing the roots out so I can see what's left over. I'm going to do long division. I'm going to divide that out. I have x to the 4th minus 6x cubed plus 6x squared plus 24x minus 40. And let me tell you, if you don't get a 0 as a remainder, you have done something wrong. Right? Because these are factors of that polynomial. You should get no remainder. Okay? So let's do that. So I do x squared goes into x to the 4th. What? X squared times x squared times x squared is x to the 4th. X squared times negative 6x is negative 6x cubed. X squared times 10 is plus 10x squared. Then I subtract. First terms fall away, which is what we would expect. We would expect them to go away. 6 minus 10 is a negative 4. X squared. Pull down the next term. Actually, go ahead and pull down the rest of the terms. We go again. X squared goes into negative 4x squared. Negative 4 times. Negative 4 times x squared is negative 4x squared. Negative 4 times negative 6 is a positive 24x. Negative 4 times 10 is negative 40. And we have a 0 remainder, which we should, because those are factors. That quadratic is a factor. So this is what I have left over right here. I would set that equal to 0 to find the zeros, wouldn't I? That's all I would do. X squared minus 4 equals 0. I mean, we know we don't even have to do anything. Can't we see what that is? I mean, we've got so much experience with this. We can see that. So we're going to find all the zeros. So the zeros are 3 plus or minus I. Those are 2 of the zeros. And the other zeros are plus or minus 2. And for me, that's a much quicker, easier way than to do the synthetic division and deal with all the imaginary stuff. Okay? How are we with that? Is everybody okay? All right.